Hello, good evening. My name is Kate Sanders with the OSU Alumni Association, and welcome to Travel Talks. Our online Travel Talks program invites experts from across the university, as well as friends of the university, to learn about places we travel. This is our last official talk of the Travel Talk season, as when the weather gets nice and the sun starts shining here in the Pacific Northwest, we notice that you all don't like to be on Zoom in the evenings. So we will take a break during the summer months and we'll head back in the fall when the rain starts again. So next fall, we'll have a whole nother series of travel talks waiting for you. But we did do a talk last night on the Smoky Mountains in Montreal and Quebec Christmas tours. So if you are interested in either the Smoky Mountains trip or the Montreal and Quebec tour, those were trip preview talks, and they are going to be posted online at this site for oregonstate.org/travel talks, with along with all of our other recorded travel talks. So this is May. It's our season for OSU Days of Service. It is a time when Oregon Staters all over the world give back to their local communities. How can you participate? Well, you all volunteer all the time, I'm sure of it. If you're on a board, you volunteer in your local homeless shelter, at a soup kitchen, or at another community organization. Just let us know. Log your volunteer hours at for oregonstate.org/service. We also have a few volunteer projects that are organized by other volunteers throughout Oregon, in California, and in Idaho. So you can join one of those existing programs. You can also donate your gently used business clothes to the Benny's Business Closet or send inspirational messages to our graduating students because, June is right around the corner where they're going to be graduating and going off. So join us this May for OSU Days of Service. Now, I always like to talk about a couple tours before our programs, and I've picked three that relate to today's talk. So next year in January, we're going to be headed to Finland. And this trip, the brochures just hit homes, and I'll tell you, my daughter is so excited. She wants to go. You get to stay in a glass domed cabin, perfect for viewing the Northern Lights, experience a dog sled ride, go snowshoeing through Midland Forest, visit Estonia, Helsinki, and much more. And this is a trip great for my active travelers who like to get out and do things. Do you love viewing solar eclipse? Well, we have one that is coming around in 2026. You can view it just off the coast of Iceland. On this tour, you'll also visit Denmark, Sweden, Norway, Scotland, and it's a wonderful cruise. So if that is your interest, there are spaces available. People have been booking this one. So you might want to check it out sooner than later if you want to catch a solar eclipse. Then the last trip to talk about tonight is Iceland in our Northern Lights. We're going to be there in October of 2026. So depending on your schedule and your calendar, whatever works best for you. So here's another great opportunity to see the Northern Lights in Iceland. And of course, go to the Blue Lagoon and Icelandic courses and see the Golden Waterfall of Gullfoss, active geysers, museum visits, and much more. So bunch of options for you related to tonight's talk. And I just remind you that all of our trips are online at oregonstate.org/travel. And we have trips loaded into 2026, and I am starting to plan 2027. So if there's somewhere you want to go, let me know. You can drop a note in chat or you can email me either way. Uh, for tonight's talk, our Q&A box is open, so you can put your questions in the Q&A during the talk, or you can also put them in the chat. Either one, I'll be here to monitor the chat questions and help Laura, our speaker, out during that. So don't be shy. We do want you to interact on this tour. So, or sorry, this presentation. So you might have a couple of questions asked for you to actually put in the chat. So please do participate as you're willing. So now we're going to move on to tonight's talk. Laura Edson is joining us tonight. She is the project manager for Aurorasaurus Citizen Science Project, and she's going to illuminate us on the science of auroras and solar activity, one of nature's most mesmerizing light shows. How is this related to Oregon State University, you might want to know? Well, OSU's Dr. Heather Fisher assists this program to evaluate it and evaluate its quality through the NASA Science Activation. So, Laura, welcome to Travel Talks.
Oh, thank you so much for
Hello.
having me. I am delighted to be here. I'm going to go on and share my screen. And I don't seem to be able to share sound.
Oh, well, let me fix that for you,
Oh, thank
hopefully.
you so much. No worries. It wouldn't be a Zoom call without one technical difficulty.
That is true. I will work on that in the background,
No problem.
hopefully.
All right, so I'll go on and share and get started. Um, my name is Laura. I am, as she said, the project manager for Aurorasaurus. I did want to point out just very quickly that we are giving this as an educational talk and it's not associated with the tours, but hopefully we'll provide you some good information about auroras. I also wanted to shout out that the founder of Aurorasaurus is attending tonight, Dr. Liz McDonald. So if there are any questions I can't answer, I will be sure to pop them to her. What we're going to talk about tonight are just a couple of different things. We'll talk a little bit about me. We'll talk a little bit about you so I can get a feel for who you are and what you're interested in. We'll talk a little bit about participatory science, which is also known as citizen science. We'll talk a little bit about aurora science and how auroras happen. And then we'll talk about our project, Aurorasaurus, and some ways to learn more about auroras. And then I will give a little quick note at the end about eclipses and an open question about auroras and eclipses. So if you want, go on ahead and let me know in the chat where you're from and what you're most excited to hear about. We'll give you a moment to do that. Right. Okay, so we have someone from Cave Junction, Oregon, somebody who's tuning in from San Diego. Fabulous. Love that. I am calling in from Maryland, on the East Coast. So, my name, again, excuse me, is Laura. I am actually not a scientist. I'm a museum educator. My background is in history. But I think that's really fun because it shows that through citizen science, all of us bring different perspectives and different assets to the study of the aurora. My favorite part of aurora chasing, which I have not gotten to do very often because of where I live in the DC area, is connecting with something in nature that's always surprising. Every single aurora is completely different and a totally different experience. Looks like we've got people tuning in from near and far. That is so exciting. Thank you all for being here with me tonight. I enjoy the most getting other people excited about things. So hopefully we'll share some of that together tonight. Now that you know a little bit about me and I've heard a little bit about where you're calling in from, I'd like to learn a little bit about you. And you can just kind of do this on your own. Raise your hand or shout out in the chat if you have seen Aurora before. Has anybody here seen the Aurora? And Alaska and Iceland, those are both incredible places to chase Aurora. My first Aurora was in Iceland as well. And in fact, on the right of this slide, that's my first picture of an Aurora. Oh, nice. Aurora tours in Fairbanks in the winter. Oh, from your deck. Karen, I am jealous. I got to see it once from my deck last May during the very, very large superstorm, which we'll talk a little bit about. It was not expecting to see it through my orange night sky in the middle of the DC area, which is, for those who know, measures of sky darkness, a Bortle 9 is heavy, heavy light pollution. And I was able to see that on a cruise in Norway and Alaska. So it sounds like we've got wonderful, experienced aurora chasers here. Many scientists have not actually seen auroras before. Raise your hand if you have, or shout out in the chat if you've encountered participatory science or citizen science before. Anybody done like iNaturalist, Penguin Watch? Karen has. Fabulous. Love that. eBird, yeah. No and no, unfortunately. Well, Lisa, we will get you some good information. I love iNat too. That's a lot of fun. Has anybody done participatory science specific to auroras before, like Aurorasaurus? Oh, a squirrel project, fabulous. Well, we will give you some good ideas for how to take part in Aurora citizen science as well. Now, who here loves nature? We want to shout out in the chat. I'm guessing so between the eBird and the Squirrel Project that we love nature here. Yeah, eBird is a fantastic program. We learn a lot from them. Yes, we love nature. Glendale app and Hello Aurora, those are both fantastic. All right. Raise your hand if you think helping with scientific research sounds fun, or shout out in the chat. Loggerhead sea turtle babies getting to the sea after hap touching. That's a wonderful project. Yes, absolutely. Wonderful. We've got some Glendale fans here. Fantastic. You all have exactly what it takes to be a participatory scientist. Because fundamentally, citizen science is about falling in love with the world more, as Sharman Russell wrote, which we think this is a wonderful encapsulation of what it means to do this kind of work. This organized research where members of the public get to engage in the process of scientific investigation, whether that's through gathering data, analyzing data, asking scientific questions, even evaluating some projects. It's a way for all of us to come together and bring our different perspectives to something we want to learn more about. It has been repeatedly proven to work on a massive scale, and it generates high quality data. So it's a very viable method of doing science. For those of you who are very interested, if you want to get involved in some projects or some other projects, you can check out SciStarter, because citizen science, participatory science covers an incredible range of topics, from penguins to phytoplankton, petrochemicals to hunting planets and comets. For some of them, you might have to find something in a photo. For others, you might play a computer game. And for still others, you might even report something in your neighborhood, like an aurora or a bird. Um, SciStarter is kind of a clearinghouse that lists out different projects, and it will help you find a project that's perfect for you. So as we transition to talking a little bit about the science behind auroras, I wanted to take a look at this picture with you all and ask you, what are some things that you notice in this picture? You can type in the chat. Different colors. Yeah, you've got some reddish color up at the top. There's almost a little blue in the middle there, and then green at the bottom. Some movement. We've got stripes. We've got this beautiful discrete aurora. We'll talk a little bit about that. Snow, absolutely. We're in a cold area. In fact, Vincent Ledvina took this picture in Fairbanks, Alaska. So it was a really great observation there. We've got some auroral pillars. Those are those structures that you see rising up. It's bright. Yeah. The landscape is snowy. The trees are the same kind of conifer. Yeah, absolutely. Stars, says Kate. And you notice that you can see the stars through the aurora. That's actually a great trick because, Amy, we love Vincent. Because one of the things that distinguishes something wispy in the sky, is that through clouds, you can't see stars, but you can see stars through auroras. So it's a great way to kind of keep an eye out for what you're looking at. Oh, it looks like there may be a little bit of that special blue. That's really great observation. We'll take a look through those colors in a little bit. Oh, excuse me, I take it back. This photo was taken in Churchill, Manitoba, not Fairbanks. All right. But what is the aurora? The aurora is this complicated dance between the sun and the earth. and people have cultivated knowledge about it for literally millennia. It has many, many different names across the world. Scientists in Western traditions tend to use a term derived from the Greek goddess of the dawn, Aurora. The northern lights are called the Aurora Borealis. Borealis means north. Southern lights are called the Aurora Australis. Australis means south. Um, the aurora is made by processes in the space between the sun and the Earth's upper atmosphere. Um, all right, we're gonna go without sound. So I'm gonna show you a little video right now. Um, and I'm gonna try and narrate it. The timing is a little bit funky, so bear with me. The sun is our nearest, giving off particles.
We actually could hear the sound, Laura, when you were unmuted. If you want to restart that, we could hear the sound.
Fantastic. Let's do that. You can hear me talk through the computer instead of through Zoom. All right. The sun is our nearest star. It is constantly giving off particles along with magnetic fields that flow out across the solar system. Scientists call this the solar wind. As the solar wind reaches Earth, it draws the magnetic field around Earth out long away from the sun. Charged particles from the solar wind get stuck in these magnetic fields and go around to the far side, like this. There, they stretch the magnetic fields out, and snap! The magnetic fields reconnect with one another in a new way. The particles are accelerated back toward the north and south poles, where they rain into the ionized upper atmosphere. They collide with atoms and molecules there to create the lights of the aurora. And when they collide, or when they come down the north and south magnetic poles, they create this oval around the poles of activity. We call this the auroral oval. And there's one in the North Pole and there's one around the South Pole. You can see here, which is some forecast images from NOAA's Space Weather Prediction Center, or SWPC, that the oval can be kind of small with light activity as on the right, or it can expand towards the equator as on the left picture when there's a lot of energy being poured into that system. So you want to kind of keep in mind getting under the auroral oval to up your chances of seeing aurora, and we'll talk a little bit about that later. As those particles come down through the atmosphere, they ricochet off of atoms and molecules that are present in the Earth's upper atmosphere. As they impact each atom or molecule, they transfer some energy to it and put it into a state that's called being excited. As the molecules and atoms calm down to their normal state, they release that extra energy in the form of light, in the form of photons. So the aurora is actually these tiny little shimmering photons being given off by many, many, many particles, kind of like a glitter bomb of charged particles, as Dr. Liz likes to say, or a like a glittering expanse. Those different atoms and molecules produce different colors, particularly at different altitudes, because they're kind of layered in the Earth's upper atmosphere. So oxygen gives off red and green colors. Oxygen red occurs above 200 kilometers, which is 120 miles. Oxygen green occurs between 120 and 190 kilometers, which is about 62 and 118 miles, somewhere in there. And then nitrogen blue occurs roughly in the same space as the green, a little bit on the upper side of that. Below 100 kilometers or 60 miles, nitrogen can also give off red and blue light, making it look kind of purple. Sometimes the aurora can also look like it has other colors in it because of color mixing. For artists in the group, it's additive color, the colors of light mixing. If you're looking through both from the ground, if you're looking through both a red and a green section, it might look kind of yellow. If you're looking through the green and the blue together, it might look a bit cyan. And the red and the blue give that kind of nitrogen purple pinky color at the bottom. And just to kind of give you a sense of the scale of all of this, I got a knitting machine last year for myself, and was playing around with it. And I went, you know what? I think I'm going to try and make an Aurora hat. And then I went, I bet I can make a scientifically accurate Aurora hat. And so I came up with this. Um, and each row of knit represents 6 miles. But I was showing it to a friend, and they said, you know what? This is actually really huge. And I went, I had never processed how enormous the Aurora is before. So let's take a look at this. Row one at the very, very bottom is where Mount Everest is and where the highest commercial aircraft fly. That's row one. This is a 50 row hat. Um, in row five, we have the highest scientific balloon. So that's quite high. We're getting higher than you would necessarily be able to breathe. The Aurora starts at row 9. Visible meteors, which means shooting stars, happen towards the middle of the green aurora. So they're going straight through the aurora there. And even higher than that, the International Space Station actually soars through the top of the red aurora, which is pretty cool. And astronauts often do take pictures of aurora from above and within, which is really, really neat. So if you think about it, the aurora is really, really high up. It's on the edge of space. It's part of why it can be seen from such great distances. And it's mind-blowing to me that when we look at it, we're really looking at something quite big, and I feel kind of small looking at it that way. When you see the aurora, as we were looking at before, you'll notice a couple of different types of shapes. There are many. At Aurorasaurus, we tend to divide up into 3 shapes. Discrete arcs, which are the ones that you see in the famous photos, where they're those beautiful ribbons rippling through the night. Diffuse glows, which are kind of cloud-like and just sort of faint on the horizon usually. Towards morning, if you're out for a late night of aurora chasing after the main show, and towards the dawn side, you might see pulsating patches that can either be very slow or they can go flash, flash, flash like a disco ball or paparazzi. And then there's subaraural phenomena. And our favorite subaraural phenomenon is Steve. Yes, there is an aurora named Steve. It stands for strong thermal emission velocity enhancement. It was noticed and photographed by participatory scientists in the Alberta Aurora Chasers group in Canada. They brought it to scientists at Aurorasaurus and Calgary. And Dr. Liz, who's on the call today, actually first authored the first modern paper about Steve, and it has sprouted its own incredible field of study. It's very exciting. Steve happens closer to the equator than the rest of regular aurora. It goes east to west, and you'll see either a mauve arc or a gray arc. And it has these really distinctive little stripes underneath it that scientists call a picket fence. So it's a very distinctive and very exciting phenomenon that tends to happen towards mid-latitudes, which are like the border between the US and Canada, or where you guys are. So keep an eye out for Steve during stronger storms. Back to May, you do actually get to see aurora in Oregon. There was aurora reported on Aurorasaurus near Corvallis, Oregon, during the May storm last year, the May superstorm, which was really exciting. And you can see they actually got some great colors there. It's not always that strong, but y'all are pretty close to mid-latitudes in Oregon for those who are there. So keep an eye out on sort of mid to largish aurora storms. You may be able to see it from there. The May storm was really significant. This is the reports that we got. We had over 6,000 reports, which is the most we've ever gotten in one storm, from 7 different continents and even ships in the ocean. You'll see one pop up. The Earth turns underneath the aurora. So even though it looks like the aurora is passing over, that's actually the turning of the Earth. And the nice thing about that is because of the way that the Earth turns, if you keep track of what aurora chasers are seeing to the east of you, you'll have a good sense for what you're about to turn into. So it's a tip for keeping an eye on the aurora. But here's the big question everybody always has. How do you see the aurora? The aurora is always a game of chance. This is not like a comet or a star conjunction or something that you can really, or an eclipse that you can really predict ahead of time. The mechanics that go into generating an aurora are so complicated. And we really often only get about an hour's heads up if aurora is likely. And so you want to kind of maximize your chances of being in the right place at the right time. You want to try and be underneath that auroral oval that we talked about earlier. Go during a time of year when the sky gets dark. The sun washes out the aurora. Just go to Fairbanks. Yep, Fairbanks is definitely under the auroral oval, and in winter it's quite dark because they get 24-hour darkness. In the summertime, however, if you go to Fairbanks, you've got midnight sun, and the sun will wash out the aurora. So you want to go somewhere where the sky gets dark. You want to find a place with a clear view towards the nearest magnetic pole. Whether if you're in the north, that would be the North Pole. If you're in the southern hemisphere, the South Pole. Make sure you watch space weather forecasts. You can check out SWPC. I always keep an eye on my local aurora chasing group. And by local, I mean the one directly north of me, because the Washington, D.C. area does not have an aurora chasing group. We barely ever see it. But the Pennsylvania group directly north of me does. And if you don't have one near you, go north, because what they're seeing might show up with you if conditions allow. You definitely want to watch your weather forecasts, because as we said before, you can't see stars through clouds. You also can't see aurora through clouds. So if it is cloudy, you might glimpse it through little breaks in the clouds, but you're really not going to see it. So make sure you got clear skies. As I said, follow your nearby aurora chaser groups and be patient. It may take multiple tries to see aurora. So when everything looks really promising, sometimes it doesn't show up. Sometimes the magnetic field is facing the wrong way, or it's cloudy, or many other reasons that it could not show up. And sometimes when we don't expect it at all, it's just like, hello, I'm here now. So be patient, keep trying. And of course, be sure to practice your nighttime safety. If you are out in the field at night for any reason, stargazing or aurora chasing, be safe, be practical. One of the things that is always surprising, and that surprised me the first time I saw my first aurora, I didn't actually realize it was an aurora because it was gray, and I was looking out the window of an airplane. Auroras look different to eyes and cameras, and the reason isn't the aurora itself. It's actually the biology of our eyes. So in our retinas, in the back of our eyes, there are two different kinds of cells that help us to see. There are rod cells, which see in black and white and are activated in dim light, and there are cone cells, which are activated in bright light and help us see in color. You can sometimes get a little bit of mix where both are semi-active at the same time, but they, because they're activating at different light levels, and aurora is pretty dim, your rods are going to be more active when you're looking at an aurora. I did get a wonderful, so it's going to, excuse me, the rods will be more active, so it's going to look more black and white. I did get a wonderful tip once from Andy Whitteman, a wonderful volunteer of ours and Aurora guide in Fairbanks, that if you shine a flashlight on your nose, not in your eyes, because we never want to shine a flashlight in our eyes, but on your nose, the ambient light will activate your cones, and for a couple of seconds, you'll be able to see the colors of the aurora. But you will lose your night vision. So it's a trade-off. Cameras, on the other hand, they have really, really good low light sensors. So they're able to see those colors in ways that we are not. And what that means is that particularly if you're at a mid-latitude, like in Oregon, if you can't see aurora with your eyes, but it might be there, take your smartphone camera, put it on night mode, and see if you can capture it that way. Sometimes you can see cameras or see auroras that are subvisual or camera only. It's a really different experience to see it in person than on film, and it's really, really beautiful in both ways. It's hard to explain the experience unless you've had it. And I know many of you today have seen the aurora, and you know that feeling of the beautiful ghostly ripples in the sky. But it's just different. We study the aurora because it can tell us a lot of different things. It reveals conditions in near Earth space that we call space weather, which is particles, magnetic fields coming from the sun to Earth. These are really important for us to study because space weather can affect very, very large technology networks like power grids. It can affect satellites. It can affect GPS. It can affect the space station. These are, technologies that are important to our daily lives. If you think about all the things that GPS does. So we have to learn more about auroras and space weather to help build in technologies that can withstand these things and to understand these dynamics in a high-tech world. They also show that the Earth has an atmosphere and a magnetic field, which is why we are here. Mars lost its atmosphere because it lost its magnetic field, and so it doesn't have the same kind of auroras that we do. So it's almost a proof that the Earth loves us and protects us. And they give us ways to investigate some of the wonderful mysteries of space. What other science questions can we ask? There are still open questions about how exactly the aurora works. It is really, really, some of the areas of study, like Steve, are quite new, and there's a lot to learn. And it's really, really exciting to feel like you're on the cusp of discoveries in a field. We still wonder, can aurora data over time help us predict solar storms? There's so many different things that go into solar storms that there's a lot to study there. Can events on the Earth's surface, like big storms, or I've always wondered about really big volcanoes, can those affect auroras? And are there other kinds of auroras like Steve's? I see a great question in the chat. You've not seen Steve in Alaska. Why is it seen more in the lower 48? Steve is caused by different dynamics. And I'll let Liz get that question too if she wants to. But Steve always occurs equatorward of the main aurora. So if you're in Alaska underneath the main aurora, it's actually going to be to the south of you. So it tends to show up in like North Dakota, right along the US-Canada border, Alberta, Saskatchewan, southern areas of the provinces there. But it always happens equatorward of the aurora. So we have Aurorasaurus to help answer some of these questions. On aurorasaurus.org, we project a scientific aurora model. It's the same one that I showed you earlier with those aurora ovals, or a very similar version of it called Ovation Prime. And it projects a view line, which is this red line that you see in the picture. That's where we expect it to be visible from. However, when you add your reports, we can recalculate that line to prove that you were able to see it below the expected line or within the expected line. And then we can validate the model that way and improve the model. We used to crowdsource reports from Twitter as well, but we are no longer able to do that. This information becomes a data set that scientists can use to study aurora. Yeah, and Liz will try and share a paper about Steve. The other thing that we offer on Aurorasaurus is a space weather chart, space weather data chart. And this is an easy way to see what is potentially about an hour away. So this This Akasofu epsilon parameter in scientific parlance, it relies on satellites that are about an hour upstream of Earth. The higher the line is, the more likely large aurora is. The lower the line is, the less likely aurora is. And you can see on this chart that the color becomes more towards the red end of the spectrum, the more strong it likely is. So it's a really, really simple chart to help you figure out what is likely in about an hour. All right. When you take those photos and upload them to Aurorasaurus, we love to see a color photo because if you remember, the colors of aurora are tied to information about their composition in terms of oxygen and nitrogen, as well as their altitude. So we can use some detective work to figure out how high an aurora is and what it's made of, which is really, really cool. It'll include phenomena like Steve, and this beautiful photo by aurora chaser Donna Locke has a meteor, it has Steve, it has, I believe, Comet Neowise down in the bottom corner there, and the aurora itself. So it was a little bit even more than a hat trick on that photo. Most importantly, we need to make sure that the timer on the camera is carefully synced. We are perfectly happy to get back of camera photos if those are quicker and easier. But it's really, really important that we know exactly what time it was taken so that we can match it up with other people's photos and with data and investigate it a little further. If you want to learn more, we do have a blog that Dr. Liz and I write that includes beginner intermediate level deep dives into different parts of the science and experience of the Northern Lights. We also have, if you want to send to friends or if you want to explore it yourself, beginner level background information in the Learn section of our website to help explain some of these concepts. Participatory science is a team effort, and it's important to us to be able to share it with people. Oh, thank you, Kate. So we have various partnerships with different fellow organizations in space weather and in education to do to create ways to make it easier to learn. So for example, we collaborated with our colleagues at NASA to create the first 3D printed model of the Earth's magnetic field, which has been a really nice educational piece to help people learn about it. We have a virtual tour, and we have a card game for middle schoolers. And on the left there, for those of you who chase in the lower 48, you may be familiar with NODAC, the North Dakota dual aurora cameras, also created by Vincent Ledvina in partnership with Live Aurora Network and Aurorasaurus. So it's a really fantastic aurora camera. That's another resource that you have is aurora cameras that point towards the aurora and will let you know if it's actually out. I'm going to speak very, very briefly about eclipses. Solar eclipses happen when the moon gets between the Earth and the sun and casts a shadow on the Earth. So when you're within a solar eclipse, you are just within the moon's shadow. The moon has an elliptical orbit that is longer on one side than the other. So when the moon is slightly closer, which is called perigee, it is large enough to fully block the sun, and you get a total solar eclipse. The last one was in April 8th, 2024. And the next big one that will be easier for us to get to is going to be that one in 2026 across Greenland and Iceland and Portugal. And we're really, really excited about that. The annular eclipse, which is a ring-shaped eclipse, is when the moon is a little further away at apogee, and it doesn't quite cover the surface of the sun. The last one of those was on October 14th, 2023, which was across North, Central, and South America. We have a question about eclipses, if anybody is going eclipse chasing. There is a type of aurora that occurs during the daytime. A lot of times when you hear short explanations of how the aurora forms in the news or in other resources, um, you'll see this story that particles come from the sun and they go straight down the funnel, the funnels at the north and south poles. Those are called polar cusps within our magnetic field. So this diagram on the right shows the Earth's magnetic field with these little funnel cusps here. That is not the aurora that we see at night. The aurora that we see at night is made through that process in the video where the energy and particles go to the night side away from the sun and then come back. This direct funneling is a type of aurora, though. It is called cusp aurora, and it is visible during the daytime. The problem is the other thing that's visible during the daytime is the sun. Cusp aurora is usually only visible from a tiny island that's part of Norway, but is way, way, way far north of Norway. It's 77.8 degrees north latitude, called Svalbard. We're curious to see if there is auroral activity, whether you might be able to see aurora during a solar eclipse. So, if you go and you point one camera at the solar eclipse, potentially with a proper filter on it, and point another camera north, we would be interested to know if you see aurora, and we'd love reports to Aurorasaurus. So now that we've talked through all of these different things, and I've just filled you with all kinds of info and facts, let's take a look at this picture again. What are some things that you notice in the picture, and what can you infer from them? And you can use the chat for this. No clouds. Yeah, that's really important. He had a really nice clear sky to look up at the aurora. The green is lower. Exactly, Amy. You've got that red, that oxygen red further up, and you've got the green lower with a little bit of that blue in between. Yeah, the reds are higher. That's that atomic oxygen up at the top. Yeah. Anything else you all notice? Somebody pointed out earlier that we have the ribbon shapes. That's the nice discrete aurora shapes. Steve, oh, I wish there was Steve. Unfortunately, this one is in Churchill, Manitoba, and it's a little too far north for Steve. Why is there no pink? That's a fantastic question. During particularly strong storms, you get a little pink border at the bottom of the aurora. My guess is that this wasn't as strong of a storm, or that the very, very complicated physics that go into the aurora just didn't give us a nitrogen pink lower border. Amy, you're absolutely right. Sometimes the colors are so bright and come together, it turns almost white. And again, that's that additive color again, where you're seeing all of these different pieces together and your eyes are interpreting that as white. Yeah. Well, thank you all so much for taking the time with me to look into the aurora and the science behind it. And I hope very much that you'll join us in Aurorasaurus when you go aurora chasing. And I'm happy to take questions.
Yes, that was amazing. Anyone who has questions, please do type them in chat. And while I'm going to let some of these questions add up here for a second,
Sure.
I had one for you.
Absolutely.
How many, on average, how many days a year are the auroras visible?
That is a really great question. And the answer is I can't really give you an answer. The aurora happens all the time, day and night, 24 hours a day. The question is whether we can see it, and the conditions to see it are different from the conditions for it to occur. So again, you've got that cusp aurora happening, you've got that night side aurora happening. As was pointed out earlier, if you go to Fairbanks, Alaska, underneath the auroral oval, during the seasons where the sky is dark enough to see aurora, you'll get aurora almost every night,
Amazing.
visibly. But is it visible from Oregon? More rarely. Is it visible from Washington, D.C.? Once in a blue moon, and significantly less than once in a blue moon. But,
Oh my
but yeah,
gosh.
it's always happening. It's just a question of our perception.
Oh, Gordon had an interesting question. He
Yeah.
wanted to know if it makes noise.
That's a really interesting question, and it's one that's been looked into for a very, very long time. We actually, Liz, if you can drop the blog post about the history of that question into the chat, that would be incredible. Um, People have investigated it. There are a number of citizen science reports throughout history of, yes, auroral sound. Uh, Citizen science reports through history of people hearing like a buzzing or a rustling sound. Yeah, Amy is reporting a buzzing in their ears or pressure. Um, the challenge is that because if you think back to the hat, the aurora is so high up that sound waves wouldn't be able to travel instantaneously. So the origin of these noises is really, really interesting, and it's an open question that
Mm.
people have been investigating. And I think Liz can add, or I can add in a couple of minutes, a blog post written by one of our Aurorasaurus ambassadors who's a historian, and who was studying these questions during the first and second international polar years. So it's a long-standing question. And if you are watching Aurora and you hear something, we would love if you would make a report to Aurorasaurus and add that to the notes because we'd be interested in gathering data on it.
I think I found your blog post, Listening for the
Oh, thank
Sound
you.
of Auroras in a
That's the
Historical
one.
Record.
Yep,
Great.
that's the correct one.
That's
Thank you.
amazing. So, what about pollution? Can
Okay.
pollution affect an aurora?
So I'm gonna punt this one to Liz, but again, there's the challenge that I find in terms of talking about Aurora is that um we tend to think of the atmosphere as like cloud level. But again, if you think back to the hat, the aurora is on the edge of space
Mm,
and it's higher than a lot of things can go. So yeah, can you unmute Liz? I think she can answer this
yes.
better than I can.
Yeah. Give me one moment, Liz, and I'll find you.
That's really interesting, Amy. I'd be interested to if you include that in reports, that'd be interesting to start gathering.
All right, Liz, you have the power to talk.
Yes,
All
thank you, Liz.
right. Can you hear me? Yes.
Yes.
Cool. Yeah, thank you. Yeah, so the pollution. Think about Laura's absolutely right. Most of the atmosphere, the really thick atmosphere that we think about is way below where the aurora is. So it's not been affected, but the very upper edge of that atmosphere does connect to where where the space weather happens, where the atmosphere is more charged up, has more charged particles, really the edge of space that's like 60 miles and up. Um, and but right below that, the atmosphere has different layers. Right below that, there's the mesosphere, which is the coldest part of the atmosphere, and it's actually getting colder as it's heating up below. Um, and there are the highest altitude clouds can be seen more frequently in the mesosphere. So
Mm.
the noctilucent clouds. So some folks may have seen those too. Um, Let me see. Oh, I was also going to say that as we are now launching more and more satellites, there's concern that rocket exhaust and other things could be affecting the balance of the atmosphere more from the higher altitudes as well. But that's again like not um, well, it's something that's changing. It's also something that's not totally understood.
That's great. Laura put her hat on. You look great.
Awesome.
So I just wanted to again give some perspective here. So on the hat, what we tend to think about as the atmosphere with clouds and planes and stuff is here. Those
Yeah.
noctilucent clouds that Liz was talking about are here. They're under the aurora. The aurora is all of the rest of this. The International
Wow.
Space Station is here. Low Earth orbit is here. So it's just
Mm,
huge and it's much, much further off the ground than we tend to think of it being.
that's really interesting.
Yeah.
That is really great. And then, say if anyone else has some questions, feel free to type it in chat. This is been wonderful. I might have missed this at the beginning, but the story behind the name Aurorasaurus.
I'm punting that one to Liz because that's her baby.
Yeah, so I came up with the name more than a decade ago when we had this idea and we wanted to get this new data out there using social media and using citizen science so that we could get more real-time alerts. And one thing we might not have said is that actually you can, when you sign up for an account, free account on Aurorasaurus, um, you can get two kinds of alerts. So one is from the model prediction and one is from people around you reporting auroras.
Okay.
So, oh my goodness, I just lost my train of thought. Sorry, going off
So
on
it's really
tangents.
great to make an account, and we appreciate that as well. We also get the newsletter, which we write ourselves.
Did
So
I answer
we
the
hear from you.
question though? What was the actual question?
Just the name, the
Oh, the
Borosaurus.
name. Oh, yeah.
Yeah.
So we were all scratching our heads and trying to come up with a URL. And, things weren't available and we wanted something catchy and we just kept, like beating our heads on the wall until finally we came up with Aurorasaurus. And the small team that I had at the time, this was a name that we all agreed was catchy and fun, and it has served us well.
That's great. So, I'll also ask another question as some other folks are trying to type some in. Um, we all know about changes in federal funding. So is Aurorasaurus going to still be funded?
We hope so.
Yeah.
As of
I
right
hope so too.
now.
That is
Yeah,
great.
I mean, yeah, we can't even really say.
Yeah.
It's still pretty early to say for NASA because we don't have an administrator confirmed yet. But yeah. Uh,
No, that's great. So so the best way if somebody wants to get involved with the Aurorasaurus is to go to the website and create an account and to join it and then just follow the postings,
Follow the postings, and if you see Aurora, make a report. And even
make a
if you
report.
try to see Aurora and don't, make a report then too. Negative reports are actually really helpful for us in terms of tracking other mitigating factors like clouds and so forth. But yeah, we also have reportathons twice a year that are events that we run. They're really fun, really friendly. We have prizes. I give away these hats. And and we spend time together, we talk auroras, and then we do some concentrated reporting.
That's
And
great.
it's really, really fun. So you can come attend our reportathons as well, and those will be shouted out in the newsletter.
Oh, that's
we
wonderful.
we also have one more
Mhm.
tier of extraordinary volunteers that are often people who are really dedicated to auroras and do want to get more involved. So we have an ambassador program where
Hmm.
people can serve as kind of a representative of their local area, or they might have some other reason that they would want to get involved with our ambassadors. And we actually have monthly meetings with the ambassadors who are from
Hmm.
all over the world because we want to get the word out all over the world. And those monthly meetings, though, most of those calls or the part of those calls where we talk to people in the Aurora world, those are on YouTube as well. So.
Oh,
Mhm.
great. Great.
Yeah,
And, and then Karen has a great question about movement. And is the wave scenes time lapse or rapid movement or
great question.
yeah.
Both. You get a lot of really wonderful photographers create time lapses of the aurora. The aurora goes through kind of a life cycle called a substorm, where it'll be very kind of quiet and building up as energy dumps into the system. And then it's almost like a bucket tipping over, where it fills up
Mm.
to a point where it all just kind of rushes out. And that's when you get that really great show. And then after that, it'll quiet down again and take several hours to build back up. So you'll you'll see a very rapid movement sometimes during that big display phase called the breakup phase. but it'll be slower at other times. So yes and yes.
Yeah.
I also see a question about whether auroral beads are the same as picket fences. I know that they are not, but I'm going to pass that one to Dr. Liz.
Yeah, so I don't know if you had a picture of a picket fence in
I did.
the
Hmm.
presentation. We definitely, so that's kind of what's seen along with Steve. It's the like green pillars that are seen sometimes along with Steve. That's the most common name for that. Whereas auroral beads can kind of look like that, but auroral beads are where you're kind of looking at an arc, and just before it breaks up and starts racing across the sky, if you're in just the right place, you might see these beads, which from the side would look tall like those pillars, but it's in amongst the main curtain of Aurora. And then it also, so it's kind of like a different mechanism. It would correspond to a different kind of wave or instability way out in space that's driving that, and then causing, and then like indicating that that instability, that rubber band is about to snap. So beads are really significant for and hard to find. Both are interesting and significant and hard to find. Um, and yeah, Vincent is starting to study beads for his thesis. So he's up at the University of Alaska Fairbanks.
Uh,
And
that's Vincent
yeah.
Ledvina, who
Oh,
created
yeah.
the camera and took that picture that we were making comments on, and is an
Mm.
Aurorasaurus ambassador and kind of does everything.
Yeah, he's
Great.
been kind of growing with us. You know, he contributed first as a teenager, and then he was an intern, and now he's, you know, a graduate student on his way to being a big shot. So it's great. But then, yes, thank you for this picture of the beads, because they are especially like regular like this. So, uh, yeah, and they can also be maybe different scale sizes, but this is the type of picture that we sometimes get where someone is here in Saskatoon, they were walking out in the field and they saw this and they snapped the picture. So, yeah, and that's significant for a couple of reasons. One is also because we have satellites out in space that might be in the right place to be kind of at the other end of the rubber band of the magnetic field line, like 100,000 miles away. So that's not usually the case, but the more observations of beads that we get, the more we can better correlate that to signals that are happening way, way out in the Earth's magnetic field, the magnetosphere. And then we can better understand when and how that gets triggered, which is a big question that people have been debating for 40 years
Long time.
since we started.
Yeah. To Amy's
That's
point, I
great.
think the thing that is most interesting to me about all of this is every single piece of information has an asterisk, but wait, there's more. So you can dive into this to endless depths. There's never a real end to it. There's always something more to discover, whether it's something on a specific topic or something related to the topic, or Steve. Suddenly there's Steve. So that's what's wonderful about Auroras is you just never stop learning.
Stop learning. Yes. Oh, I have one more question, and because we're
Sure.
getting to 6:30, and I was just thinking about it. With solar flares, when we have
Mhm.
solar flares, there tends to be interruptions with data on Earth. Is there in data transmission? Is there ever any sort of interaction with auroras that we would have here on Earth, kind of similar to that?
But that's a great question. The and Liz, you can jump in if I'm wrong, but solar flares and the things that cause aurora are actually separate phenomena. A
Mhm.
solar flare is a burst of light, kind of like a camera flash on the sun. It can herald a coronal mass ejection, which can cause aurora, which is a particulate and magnetism. that launches off of the sun. So we look to solar flares to see, oh, maybe there's a CME or coronal mass ejection coming after that. But flares in themselves don't cause auroras. They can interrupt radio waves. CMEs and other space weather that's related can cause interruptions to very, very large electric networks. So it's not going to fry your cell phone, but because power grids are very, very large, it can impact power grids. And it can impact tiny, tiny electronics. It can impact like minuscule. It can impact satellites in space. And it can send radiation through to places that are, well, what it does is it squashes the Earth's magnetic field. So if satellites and the ISS are within the Earth's protective shield, this magnetic field, they're fine. But if a big enough CME comes, it can kind of actually squash it so that these satellites and the ISS are outside of the Earth's magnetic field.
No.
Nope. Okay.
You were
Liz,
so awesome.
okay.
But the ISS is not going outside the Earth's magnetic field.
Okay.
It's
Okay.
it's geosynchronous orbit where it can get squashed to within geo. And so satellites that are in geo, which are often different kinds of satellites, but they're like way, way outside, um, people aren't in geosynchronous orbit. But yeah, but it can be, yeah, there's all different effects. That's why space weather gets very complicated and very confusing. And
Yeah.
at Aurorasaurus, we usually stick to like we stick to trying to help people see aurora and understanding the aurora, the science of the aurora, because there's like enough going on with all of that that certainly intersects with all the other timescales and types of activities as well. But yeah.
The data that we gather is for the purpose of helping to refine models, which in turn help us to understand space weather better.
That's great. Wow. This has been an amazing presentation. Thank you both. And Liz, thank you for joining us on this. Really appreciate it.
Yeah,
It is
thank you.
great. So, and in chat, you may have seen that Laura put the email address of for Aurorasaurus. If you have any more questions, feel free to go ahead and email them, and we'll share that as well in our follow-up email to everyone who registered for the talk, and as well as these other links that were dropped in chat too. So we'll be sure to send all that information out in our follow-up email. And just to close us off for this evening, I just want to remind everyone where you can find us at fourOregonState.org/travel. And you can find all of our tours there. Of course, we're on Facebook. If you are, we are there as well too. And just want to say again, thank you very much, both Liz and Laura, for joining us this evening for tonight's travel talk.
Thank you so much for having us, and thank you everyone for being here with us tonight. We really appreciate it.
Yes. All right. Well, good night, everyone, and we will see you in the fall. Goodbye.
Thanks.